right, so let's discuss quantum cryptography. Maybe we start with few words about classical cryptography, right? Because cryptography, as we know and use it today, has nothing quantum apart from very few people who can afford it. So in classical cryptography, there are two different and both very important notions to use cryptography. One is so-called public key systems, and these are in fact the system that we use all the time. For instance, when you buy something on the internet. Okay, so I'm not going through the detail here of what this is. The most well-known system here is called RSA for reversed Shamir, and okay, the last one I have to say I don't remember. But essentially, it's the idea of public key is that you know, of a safe. Think of a physical safe, a box, right? And so when you buy something to a provider, essentially what is going on is that the provider will send you a safe, okay, a box that is open, and that box, you will put your secret in it. Could be your credit card details, for instance, and then you as a user, you have a way to lock it, okay? So you could not open the box because you don't have the key, but when the provider sends it to you, the box is already open. So you can just put your secret in, and then you lock it, and then you send it back. So the box is now locked. So in principle, an adversary cannot open it. And you send this box to the provider, and the provider has the key, right? And then they can open the box and see your secret, okay? So these systems, they are, so all this encoding, if you want this box, this key, this, you know, closing the box, this is done digitally, right? With bits or calculating functions. And in fact, the main function that is used here is essentially, so this relies on factoring. So, okay, this is a bit vague at the moment, but what this means is that when you send the box with your secret in it to the provider and the box is locked, it is difficult for an eavesdropper to open it because to open the box, the eavesdropper has to solve a factoring problem. Okay, so they receive a big number n, and out of this, they have to find the factors p and q, which are large prime numbers, right? So remember this example, if I give you two prime numbers, it's very easy to multiply them. So this way, this is easy. But if I give you the product, find the factors, this is difficult, okay? Now, when we say it's difficult for a classical computer because all known algorithms are essentially exponential in time with the size of this number here. However, if you would have access to a quantum computer, factoring becomes sort of efficiently solvable, right? So there is something called Shor's algorithm that can solve this problem of factoring efficiently. So that means in polynomial time with respect to the size of this number here. So this is what we are going to discuss, in fact, next. So quantum computing. So at the moment, you have to believe me that something like this exists. Okay, and so you see now the rise of the quantum computer now, well, it puts, you know, big challenge on cryptography because, you know, at the moment, RSA and generally public key schemes are secure because for an eavesdropper, solving the factoring problem is difficult, right? But with future quantum computers, it might become easy, right? So you may want to move away from these type of protocols. Now, so this brings us now to a second type of protocol for classical cryptography. And this is something quite a bit different called the one-time pad. This is actually something much older. And in a sense, it's again based on the idea of the lock, the padlock, right? But you know, contrary to the scheme of public key, that scheme here of, oh, sorry, why did I write that? So yes, what I wanted to write first is that this is a private key system, okay? And the one-time pad is the perfect realization of this idea of a private key. And this is a system that is wonderful because it's sort of, let's write it like this, it is fully secure, okay? Or unconditionally secure. So how does it work? Let's see. So we have A and B, as usual, who would like to, so A would like to send a secret to B. And now you see what we have here is that we have something available that is of very high value, namely this is a private key. So what this means is that I have a key which I will represent in binary notation. So this is a string of bits. Let me write something like this here. And this key, it is private and it will be shared by both A and B. So let me recopy it here. Okay. Now Alice has a message that she would like to send. Again, I write this message in binary. Okay. And now the one-time pad is a wonderful solution to the problem of sending this message from A to B without an eavesdropper here now who sits in the middle being able to, you know, to reconstruct the message. Okay, it's only Bob that can reconstruct the message and Eve will know nothing about it. All right, so here is how you do it. This is the protocol of one-time pad, is that now you compute from the message and the key, you compute the encrypted message. Now the encrypted message is just here performing the bitwise addition, modulo 2, right? This is always binary here. So 1 plus 0 gives me a 1, 1 plus 1 gives me a 0, 0 plus 0 gives me a 0, 1 plus 0 gives me a 1, 1, and 1, okay? And so on. Now it is this encrypted message E that will be sent over to Bob, okay? So Eve can intercept and read this encrypted message. She can, however, not change it, okay? So the general scheme that we are going to consider is the fact that, you know, so A and B communicate via classical channel, which Eve can perfectly read. But there is always, so there is always a way for A and B to authenticate themselves, okay? That means that when B is listening to what A is saying, so when A reveals the encrypted message, Bob can trust that this message really comes from Alice, right? So as an image, you could think that Alice writes this encrypted message on a web page, okay? And Bob can check that because he knows the address of Alice's web page. So Bob can check that the message does indeed come from Alice, okay? All right, so now we have this encrypted message that is going to Bob. So we can rewrite it here. This is a 1, 0, 0, 1, 1, 1. Okay, and now to end our one-time pad protocol, now Bob, from the encrypted message and the key, will reconstruct the message. And now it's very simple. I do again addition modulo 2. So I have a 1, a 1, a 0, a 1, a 0, a 0, and so on. Okay? And it's clear why it works. It's because, in a sense, from the message of Alice here to the final decoding of Bob, well, I added twice the key, right? Once on Alice, once on Bob. And the point is that this key is random. Okay, so this must be fully random. And also the key must be as long as the message. Okay, this is important. Let's come back to that in a minute. What I was saying before is that, so we have this fully random key, which is added twice to the message. So it's clear that from here to here, essentially nothing happens, right? And so the reason why we added this key here, it's clear, right? Because so the key, so key is there a question? Ah, no, okay, sorry, I heard something, so don't hesitate, shout if something is not clear. So here, because the key is fully random and as long as the message, from this it follows that Eve cannot extract any information about the message M from the encrypted message. Okay? Okay, and that is because, so since Eve does not know K, right? So remember, the idea is that the key is private. It is only known from A and B. And therefore, you see that if I add this fully random key, which is as long as my message, then essentially every bit of the encrypted message looks random, right? And it looks random, of course, if you don't know what the key is, right? But that is the assumption that we make for Eve here, right? So Eve does not know the key, and therefore she cannot gain any information about the message from the encrypted message, okay? However, Bob, who knows the key, can perfectly decode it, right? So that's the idea of the one-time pad.
Sorry, but what if Eve copies the encrypted message and creates another message with the same length, and then Bob will subtract the key and he will receive another message?
Yes, so this is a good point. So what is very important in cryptography is that Alice and Bob can authenticate themselves, right? So when Alice reveals the encrypted message, Bob can read this encrypted message and Eve cannot change it, okay?
Okay.
You see, the reason for that is that if you would have a situation, let me draw it here. So if you have a situation where Alice talks with Eve and Eve talks with Bob, okay, but there is no direct communication from A to B, okay, well then you can probably not do cryptography, okay, because Eve can agree whatever with Alice and then whatever with Bob, but there is no way for A and B to check that, you know, that they agree on something. So in that case, this is just a no-go. Okay. Here you cannot do anything. So you always need a way for Alice and Bob to authenticate themselves, right? So I think think of the web page example, this is a pretty good one. So if you look at the right address, well, then you know that essentially, okay, it's an assumption, but okay, the assumption will be that in this sort of safe place, the information that is provided is really coming from Alice. Okay.
Okay, thanks.
But it's a good point. It's a good point that this is something that you need. So I see that there was a question in the chat. The question is now, can I read this question? No, this is... So perhaps can I ask the person who had the question in the chat just to say it through the microphone, because somehow I cannot access it.
Là, on m'entend ou pas?
Oui.
So the question was, do we have no handshake between A and B for a private key? So
do we have what, sorry?
A handshake in the terms of informatics is just before that we have the communication, we have to set some settings up, like the key between the two person who wants to communicate. So
yeah, okay, I think I see where your question comes from, and indeed it's a good question. It brings me to the next point. So what is somehow the difficulty, or what does it require to implement this one-time pad? Okay, so to implement the one-time pad, which is, by the way, a perfect solution, right? Because what I wrote here, you can prove it mathematically. Okay, so this is in full rigor. Now, again, what you need for this one-time pad to be doable is you need this authenticated channel for Alice to announce the encrypted message. And you need something even more important and more difficult to establish, which is this private key, right? So imagine that A and B never met, right? So how are you going to establish a private key from A to B in a way that is oblivious to Eve? Okay, so Alice has an authenticated channel, right? So Alice could write on her web page, this is the key. Of course, this doesn't work because Eve can read that, right? And so you can actually prove, again in full rigor, that in classical information theory, there is no protocol that allows you to establish a private key between A and B if A and B have nothing in common to start with, okay? So you see that's the very strong limitation of this one-time pad, right? So to give you an example on how to use the one-time pad, so during World War II, right? So the Nazis and the Allies as well had submarines going, you know, all through the oceans, and so of course the generals of the army wanted to send messages to the submarines, right? And these messages were sent by radio, so they had to be encoded, right? And so the way they did that is that for every day there was a code, namely a key, right, to be used. And every day you have to change the key. And so before leaving the harbor, right, each submarine left with a huge book of codes, right? And so that's a way in which you could think of implement the one-time pad, right? But of course, in this case, Alice and Bob have met in the past, right? Because Alice and Bob need to share the same book with the same codes. Does it answer your question?
Well, okay. So.
Is this a yes or a no?
Yes.
Okay, we can discuss it later if you still have questions, but that's the idea, okay? So now we have identified, right, what is the main problem of the one-time pad. It's the distribution of the private key. Now, notice that this is not a problem in public key cryptography. There, you don't need to have a private key because the key is public. Okay, the provider can send out the safe in which you put the message. But then here you see the security is then only of computational nature, right? That means it's based on the assumption that the eavesdropper has limited computational power. In particular, that the eavesdropper cannot solve the factoring problem easily. So, so far this was a reasonable assumption, and so, essentially all systems are based on public key, because if you buy something, on a company that is on a continent, that of course you have never met them, so you cannot make a private key scheme, but you have to go for the public key. But if you want something better, you have to go for the private key. But now the challenge is how do you share this key between two observers that have never met? And classically, as I mentioned before, there is no solution to this. You can prove mathematically that this is impossible, right? But quantum mechanically, it is possible, okay? And so this is why quantum cryptography is in fact, it has a more technical name, which is quantum key distribution.
Can I ask a quick question about the classical case?
Yes.
So from what I understand, in communications theory, information sources are probabilistic. So even if you do manage through some past contact to establish a common key, how do you send the exact encrypted message that you need to?
Well, you could say, so this comes back again to this problem of authentication, right?
Okay.
So you need that Alice has a way to send this encrypted message to Bob in a way that is authenticated, okay, where Bob can be sure that this comes from Alice. Then this could be on a website, for instance, or it could be via the telephone. Okay, you see what I mean?
Yeah, I see what you mean, but I guess theoretically, I'm still confused about how you can produce exact messages if you have a probabilistic information source, which seems to be a prerequisite for communications theory. But maybe that's for another time.
Well, I don't know what you mean by probabilistic. I mean, so like, you see, for now, I have a message for all of you, yeah. And I'm sending it through you, right? And you understand, well, I mean, up to technical subtleties, you understand what I mean, right?
Right.
So the fact that, I can make myself clear means that obviously it's possible to send information, right? So now, if I can do that, I can also send you the information about an encrypted message, and you can look at this page here. And so this is my encrypted message. Mm-hmm. And you can copy it, and then you can do this, right? Now, I don't know, maybe your question refers to the fact that communication channels are noisy. Okay, so that, so for instance here, I wrote something, but of course, what you can read out of this is limited by the resolution of my camera, and so on and so on, right? And in principle, it could even be that there are errors here, right? However, correcting errors in communication, this is possible, for instance, using redundance or things like this.
Okay.
Was this the nature of your question, or?
Somewhat. I was just thinking of very basic Shannon theory, where you have an information source and with certain probabilities it produces symbols. And so you have a set of possible messages. Mm-hmm. And so I was always confused about, well, if you want to send a very particular exact message, but the source only produces symbols with certain probabilities, how can you reproduce an exact message? But yeah, that might be for another discussion then.
Mm-hmm. Well, I mean, of course, but okay, you see, I mean, I know here what I want to write,
Right.
okay? So I can write it in a way whereby you will be able to read it with essentially no error, right?
Okay. So you set the probabilities to match as closely as possible the message you want to send.
Yeah, I mean, for me, there are no probabilities because I know exactly what I want to write. So
Right.
this string here that I wanted to write has probability 1 and all the others have probability 0.
Okay.
Now, from your point of view, it's a little bit different, no? Because a priori, you didn't know which string I wanted to write.
Okay.
Okay, but okay, I see your question, but I think this refers to other types of problems. And we will discuss them when we look at classical information theory and Shannon theory.
Okay.
Okay. All right, so let's go back to quantum key distribution. And so the idea will be that we will be actually, so when we say quantum cryptography, this includes actually the one-time pad, okay, which, as we discussed before, is a perfect solution if you can establish remotely a private key. Okay. Now, quantum mechanics, in fact, allows us to do that, and that's the idea of quantum key distribution, right? So remember that everything we are doing here is to distribute a key, right? The communication of the secret message that will then come in a later time. But of course, we will not discuss it here because I already told you how it works. All right, so you know, in a nutshell, you can understand the intuition as to why it is possible quantum mechanically to distribute a secret key while it's not possible classically. This is because Alice will be sending quantum states to Bob, okay? And in particular, these quantum states, they will be chosen among a set of states that are not orthogonal. So that means that if Eve tries to intervene, right? Well, if she wants to extract some information about this key or these quantum systems, she has to make a measurement. But of course, the measurement will, you know, disturb the state of the system, and that is irreversible. Okay, and so so when Alice, so let's draw it here. So when Alice sends now quantum systems to Bob, okay, and Eve attacks here, okay, all the information about the states, so let's imagine that there are some states here that are used for that. All the information that Eve acquires on these states will introduce a disturbance to what Bob is going to see, right? So Bob will perform some measurements. Maybe let me write some sigma z here, for instance. And so that's the main idea, right? So it's essentially the uncertainty relation, right? So the fact that any quantum measurement that gives you some information, or here gives some information to Eve, will have an impact on the state of this quantum system here. And any disturbance here will in fact be visible to A and B, and therefore A and B can detect the presence of a potential Eve, okay? And so if that is the case, right, then they will abort. Now, this is of course not a problem, right? Because everything you try to do here is to establish the key, right? So of course, if you would already encode some of your secret message in these states and Eve could get information about it, that would be bad, okay? But remember here, we are just establishing the key and the key is chosen at random. So even if Eve knows something about the key, as long as you make sure that you are not using it later on, this doesn't matter, right? And on the contrary, when you establish a key and you check that there is essentially no Eve on the channel, well, then you can establish a perfect key in the end on which Eve will know nothing. And then you can use that key for the one-time pad. All right, so that's the idea on how it goes. So now we are going to look at the protocol, which is the first QKD protocol, but it's still the most used today. And this is called BB84. Okay, so that stands for Bennett plus Brassard in 1984. Okay. So this discovery has also a astonishing story. So Bennett and Brassard. So Bennett, we know already who it was. It's physicist that was concerned with Maxwell's demon and problems like this. Brassard is some computer scientist. I guess at that time he was very young. And the story is that these two met in a conference in India somewhere. So, in a nice hotel. So they met at the swimming pool and then they started discussing. Okay, and they came up with this idea that was then eventually published in the proceedings of that conference. So some very obscure publication, if you want me to summarize. And so that also had the impact that for almost 10 years, this idea went essentially unnoticed. Okay, and it's only in the 90s that someone else somehow rediscovered it in a slightly different way. And then the thing became sort of well-known. Okay, so here is the protocol that Bennett and Brassard imagined, and it works in several steps. So the first step is the encoding plus the decoding. Okay, so I will give it to you in a sort of rather dry and mathematical way, but later on we will play a bit with the protocol. So here is how it goes. So Alice first chooses the key. Okay, so she generates the key to be used. In fact, sorry, maybe I should not say it like this. This will not be the key yet, but Alice chooses a random n-bit string. Okay, the final key will be obtained from that. Okay, so it's not yet the key. At the same time, so Alice chooses a random n-bit string. Sorry, maybe let me write key here. Random string R, and this is for the choice of basis. Okay. All right. So this must be pretty cryptic at the moment, but it will become clearer now. So in every round, okay. So we have. You see, this is something that we do in a sequence, right? We do many times, and because we have n-bit strings, and in each round we will essentially encode 1 bit of this string here. So here is how we do it. So in the round J, so we look at the jth component of this n-bit string R. So if this is 0, well, then A encodes the key bit. I didn't give a name to this one. Let me call it K, okay? And maybe I write these as vectors. So then A encodes Kj, right? So the jth component of the key. with the Z basis. Okay, so what that means is that if kj is equal to 0, then Alice sends a qubit in the state 0. Okay, and if kj would be 1, then A sends the qubit 1. Okay, so in every round of the protocol, Alice will be sending 1 qubit to Bob. Okay, and the state of that qubit will depend on the value of the bit string, okay, but also on this other variable here, Rj, which is the choice of basis. Okay, so here we did the first case, and you can sort of imagine what is going to happen in the second case. Let me put it like this. All right. So in the second case, so if Rj is equal to 1, then A uses the X basis. Okay, so the idea of the encoding is very similar. So that means that if kj is equal to 0, then A sends the state plus, okay, and if kj is equal to 1, then A sends the state minus, okay? And remember that plus minus, they are just the superpositions of 0, 1. Okay. So now here we have something important, okay, to notice. So A sends 4 non-orthogonal states. Maybe one should say possible. So in each round, of course, she sends 1, okay? Which one is determined by these different variables here. But from the point of view of Eve, right, who doesn't know neither what is the key nor what is this choice of basis, well, from her point of view, she receives 1 out of 4 states, 0, 1, or plus minus, and she doesn't know which one that is, right? And so because they are not orthogonal, we already know that Eve cannot tell deterministically which one it is, okay? All right, so now we come to Bob. Okay, and so so Bob, in total, he will receive n qubits, right? 1 qubit in every round, and then he will measure each one, and measures each one either in the Z basis or in the X basis. Okay, and again, this is a random choice. Okay. So the point is, Bob, now so for every qubit, he makes either the Z or the X measurement, okay? And so in every round, he gets a result, okay? So Bob gets a binary result, okay? So maybe we say like this in each round. So In total, he has now an n-bit string. Let me call it k prime. All right. Good. So the next step now is that, so now this is the exchange of quantum systems. Okay, so in every round, Alice prepared 1 out of 4 possible states, and Bob measured each one in either the Z or the X basis. Okay. Now, so what do we have? Okay, so what do we have is that we have a key for Alice. Okay, and we have somehow a decoded key K prime for Bob. Okay, and so we would like now to compare these two. Now, of course, you see the first observation is that it is clear that whenever Alice and Bob chose the same basis, well, then essentially K and K prime will match in these for these rounds. Okay. Why? Well, because Alice, you see, encoded the information about the key 01 by sending 2 orthogonal states here. Let's imagine it was the Z basis that was used. Now, if Bob measures also in that basis, well, then the result of his measurements allows him to say if the bit value was 0 or 1. Okay, and this bit value, you will find it exactly in K prime. So another case would be that Alice used the X basis, and if Bob used also the X basis, well, then it's the same thing, right? Because the 2 states sent by Alice plus minus, they are the eigenstates of X, and therefore the bit encoded by Alice in this can be perfectly retrieved by Bob, and it will also be in K prime. Now, of course, because Alice and Bob, they both choose at random their basis, it is of course not guaranteed that they will pick the same, right? In half of the cases, in fact, they will pick different bases. Now, when that is the case, in fact, the statistics will be completely random. So that means that K prime will have no correlation to K. And the reason is that, so imagine that Alice chose the Z basis, so she sent one of these 2 states. And if Bob measured X, okay, well, then it doesn't matter which state that is, but for both of them, the statistics will be random. Okay, so then there will be no correlation between the result of Bob and the bit encoded by Alice. So that gives us the idea of what we should do next, right? The idea should be that Alice and Bob should compare the basis they used. So for every of the n rounds, they will announce their basis choice, and then they will keep only those that are the same, okay? So this is a step called basis reconciliation. Okay, and so so Alice and Bob announce their choice of basis, and this is done for each round. Okay, so if you want, Alice will announce this vector R here, okay, and Bob could, just answer by saying yes or no, whether he chose the same basis or not. And the point is now they will discard, so they are going to discard all cases where they chose different bases. So they discard all rounds where they chose different bases. Okay. All right. So then after that, they keep. So what they are left with, okay, is essentially n over 2 rounds. Okay. And so here I write, so this gives sort of new keys, if you want, to Alice and Bob. So it's no longer K and K prime, but this is what we call the sifted keys. Let's call it, maybe let's call it A. And so A for Alice and B for Bob. Okay, and A and B, they are bit strings of length n over 2, more or less. Okay. All right. Okay, so maybe one thing that I should already notice immediately now is that you see, so again here we make use of the fact that there is an authenticated channel between Alice and Bob, right? And this we will always need. Also in quantum cryptography, there is no way to make it work if you do not have an authenticated channel. Okay, so again, when Alice and Bob reveal their choice of basis, they can trust each other. But of course, Eve can also listen to this conversation, right? So she then knows now everything about the basis in which all the qubits were encoded. You know, a priori that could be a problem, but remember, if we go back, let's go back one step here. If we go back to our protocol, remember, so Eve now learns this R, okay? However, this R is chosen at random, and in particular, it has nothing to do with the key, right? It's really chosen independently. And you can see it in a different way because imagine the key bit is 0, right? So this key bit of 0 could be encoded either in the Z basis via the qubit state 0 or via the X basis via the qubit state plus, right? So if you just know that this basis or that basis has been chosen, okay, well, you cannot tell what was the bit value, right? So every bit value is as likely for the Z basis or for the X basis. So this basis reconciliation does not provide any information to Eve, okay? Now, you should also note something else. It is very important that this basis reconciliation is done in the end, okay? Because you cannot announce the choice of basis before sending one of these 4 qubit states, okay? Because if Eve knows if it was that basis or this basis that is used, then she could, of course, measure in that basis or that basis. Okay, so with this extra information, you would make the states actually distinguishable, and so Eve could get information. What is very important is that when Alice sends the qubits, okay, she does not announce yet the basis. Okay, so from the point of view of Eve, she does not, I mean, all these 4 states are equally likely, right? And therefore, she cannot choose to make a measurement in this basis or in that basis without necessarily introducing errors. Okay, this is what we are going to see in detail in a minute. Okay, does it make sense so far? Okay, no comments, so I guess means yes.
Sorry, I just have a question about the end. So I thought that since they only keep the bits that they have chosen the same basis, then A and B should be the same string.
Yes, you're totally right. So if everything is perfect, so in the ideal case, we have that A is equal to B. That's totally correct. Okay.
Okay. Okay.
But of course, you know, Alice and Bob cannot assume from the beginning that everything is ideal. You know, the ideal case would be that there is no Eve. So the point is we need to check this. Okay.
Okay, I see. Mm-hmm.
So in the presence of Eve, okay, or the potential presence of Eve, so this condition, or this property, if you want, must be checked. Okay, and this brings us now to the next step. So the next step is the to estimate the errors. Okay, estimate errors. Now, so as Mona mentioned before, so if everything would be perfect and there would be no Eve, well, then we know that the sifted keys of Alice and Bob must be the same. Okay. Now, in practice, of course, things are not so easy, right? Because first of all, you could have an Eve, but in practice, you may also have errors that are just due to the technical imperfections of your devices. Okay, so so from the point of view of Alice and Bob, there is no way to tell if an error is due to imperfect devices or to Eve. And in fact, here we will be very conservative. Every error will be associated to Eve. Okay, so Eve could, in principle, you know, because the assumption is that Eve is essentially arbitrarily powerful. So even if the channel between Alice and Bob is imperfect, the channel by assumption in cryptography is controlled by the eavesdropper, right? So Alice and Bob, they are only in their separate labs, but everything that is between Alice and Bob, this is controlled by Eve. And so Eve could, in principle, you know, use a perfect channel from A to Bob on which she can then spy, right? So that's why all the technical imperfections, all the errors will always be given to Eve, right? We will make it very conservative. So now, so that's why we need to estimate these errors, right? Because the more errors we have, the more knowledge on the key Eve could have. So here is how we do it. So Alice will select subset of A. Okay, so typically this will be a small subset. To estimate let's call it like this, the error rate. Okay, so how frequent there are errors. So the point of view is, so the idea is that she will tell, so she tells Bob which key bits she encoded. Okay, so she will really reveal the key for those particular rounds. Okay, so this is a subset of the sifted string A. And then Bob will compare, okay, what he decoded. So she tells Bob which key bits she encoded, and Bob compares. So in this way, they can estimate the quantum bit error rate. Okay, so this is a quantity that we call the Q bar for quantum bit error rate. Okay, so this gives an idea on how good was the transmission of the qubits from A to B. Okay, and so if this fraction of bits where an error occurred is very small, so then the intuition is that, you know, everything went almost as in the ideal case, right? Because you can estimate how close these two bit strings are. And you see, the intuition is that if they are very similar, well, then you will, you know, on the remaining part of A and B, right? So not the part that you have used here for this estimation of the error, but on everything that is left, you will be able to perform some post-processing in order to extract a perfect key in the end, okay? However, if the error rate is too large, and we will see later what too large actually means, then you see, you know then that you are relatively far from the ideal case, and so it might be that these errors were introduced by the attack of an eavesdropper, right? And so therefore, because we can no longer provide a proof of the security for these keys, then we will abort. Okay, so let's write this. So if a too large fraction of bits are different, so that means if the Q bar is too large, Alice and Bob abort, okay? And so otherwise, so if the quantum bit error rate is below a certain threshold, oops, sorry, let me move this up a bit. So otherwise, they will go on and they will finalize the protocol with two more steps, which are, so they perform error correction and something called privacy amplification. In order to get...
Sorry, I think there is a message on the screen maybe.
Ah, yes, you're right. No, sorry, I have to do it here, of course. Okay. Yeah, sorry, this is... no, I cannot access. Okay, thanks. So they perform these two final steps of error correction and privacy amplification to get the final key. Okay, the final key is the one that you will use in one-time pad, and this key is typically much shorter than n/2. Okay, n/2 is the size of the sifted keys, but remember, from the sifted keys, you need to take out a little bit in order to estimate the errors. Okay, so maybe you take, of course, it depends on the length of these, right? But typically you could take out 1% or something like this. You just need to have good statistics, right? And so then, so this reduces a little bit the length of the sifted keys, but then when you do this error correction and privacy amplification, these are necessary steps where you will further lose bits. Okay, so the final key will typically be quite a bit shorter than n/2. But on the other hand, you know, we don't care, because our goal is to have a final key that is perfectly secure. If we need a key of size 1 million or 10 million, well, then we just know how many rounds of quantum key distribution we have to make in the very beginning, right? How many qubits we have to exchange, because we know already what is going to be the shrinking factor typically. All right, so I guess here is a good place to stop for a couple of minutes. Let's do maybe like last time, like five or 10 minutes break, and then we continue. Of course, if there are any questions, I'm happy to answer. Okay, so no question. Then I will maybe just cut this here, so then I can pause. Okay. No, sorry. I have to do this now. Ah. Okay, so we just went through the BB84 protocol from beginning to end. There are certain steps that we sort of didn't explore. So in particular, this error correction and privacy amplification. And I'll come back to that in a minute just to explain you roughly what it is. These are just classical post-processing, so it's relatively easy. But we will first discuss, so at least give an intuition as to why the protocol is secure. Okay, so why is the protocol secure? Okay, because everything so far was sort of qualitative, right? We said if Eve tries to measure, she will disturb and so on, but okay, is the intuition, you get it right, but you need to understand better why it works. So what we are going to do here is to consider one possible attack of Eve. Okay, and this possible attack, it is called intercept resend. Okay, so here is how it goes. So Alice, so we will look at a specific round here. Okay, so let's assume that Alice prepares the state 0. Okay, so this means that the bit value kj is 0 and that she chose the Z basis. So now this is sent to Bob. Oops. Okay, but in the middle there is Eve, right? So Eve is here. So she intercepts the communication. And so one sort of relatively natural attack for Eve would be somehow to mimic what Bob is doing in the protocol, right? So, so Eve will make a measurement on this incoming qubit here, and that with a measurement that will be either in the Z basis or in the X basis. And this choice, I mean, Eve has to do it randomly because Eve has no idea which basis was used by Alice, right? This information here is only revealed later on. So here we have a choice. And this choice will be that either Eve uses the Z basis or she uses the X basis. Now, if she uses the Z basis, you see that in fact she uses the right basis, the same as Alice. So then when she makes a measurement, she always gets the result +1, okay, for the measurement. And that corresponds to the eigenstate 0. Okay, she correctly identifies which qubit state was sent by Alice. And so then, at this point, well, she needs to send back something to Bob, right? She cut the communication here. But of course, if Bob sees no qubits arriving, then he knows immediately that something is going wrong. So then what Eve is doing is that she is just saying, okay, I made a measurement and I guessed that the sent state was 0. So now I just send that state again to Bob, okay? So imagine that these qubit states are encoded in polarized photons. Eve makes the measurement here, and then she just sends another photon with the corresponding polarization to Bob, okay? So this now goes to Bob. And Bob, well, as we discussed before, Bob has two choice of bases. But of course, if he would measure the X basis here, this is wrong, right? So this case will be discarded in the basis reconciliation. So if we want to make a meaningful analysis here, we have to look at the case where Bob uses the Z basis as well, right? And so now when Bob measures the Z basis on this incoming state 0, well, then he will find the result +1. So here he makes Z, he gets the result +1. So he will conclude that, let's say, maybe I should have, sorry, maybe let me write AJ here, okay? Because this will be part of the sifted key. So here I will write BJ equal 0, okay? Does it make sense? Okay, good. Now let's look at the other case, right? So here, Eve is measuring in the wrong basis, okay? And now, so the eigenstates of X are the ± states. And so when I do a measurement in that basis on this incoming state here, well, then the statistics, they are random, right? So Eve may see the result +1. So then the projected state would be plus, or she could see the result -1 and the projected state, would be a minus, okay? Yeah, sorry for this, this is a minus state here. And now, okay, so in both cases, well, she will always do the same procedure. She will just forward exactly that state to Bob, who will measure it in the Z basis. So Bob in the Z basis here will get again random statistics because the state plus is not an eigenstate of Z, right? So Bob will get the +1 result or the -1 result. Okay, if he gets the +1 result, he will decode BJ equals 0. If he gets -1, he will decode BJ equal 1, right? And so let's do the final case here, up. So here Bob makes the Z measurement. So again, he can, so minus is also not an eigenstate of Z and will give random statistics. So I have a +1 and I have a -1. And here I get a BJ equals 0, and here I get a BJ equal 1. All right? And so now you see what's going on. Well, the point is that there are lots of different cases, first of all, right? And so the point is that some of these cases, in some of these cases, Bob decodes the correct thing, right? So BJ should be 0, right? So if Eve was not there, BJ should be equal to AJ, so it should be 0. So this is correct, this is correct, this is correct. But now we see, because of Eve's attack, there are two cases here that are wrong, right? So these are cases where Eve introduced an error, okay? And again, once the basis reconciliation is performed, remember that Alice and Bob, they estimate the errors. So if Eve would perform this attack in every round, this would necessarily lead to the detection of errors, right? So now we have to estimate how frequent these errors are. And so in order to do that, we need to calculate the probabilities for Eve to introduce these errors, okay? So this is easily done via this little tree here. So first of all, we have to associate probabilities to this first choice of Eve. And as we argued before, Eve has no idea of what basis Alice used. So this is just a 1/2 choice here. Okay, this is random. Now, if I follow the upper branch here, you see that here there is nothing random anymore, right? So because Eve chose the right basis, so she measured the outcome +1 with probability 1. Then she forwarded this to Bob, and Bob measures this here also in the right basis. So with probability 1, he gets the result +1. Okay, so the final probability of this case here, this is 1/2. Now let me go to the lower branch where things get more interesting. So here, Eve made the measurement in the wrong basis. And so the statistics here of the result is random. So there is a probability of 1/2 here and 1/2 there. Now Eve now forwards to Bob some state that is not an eigenstate. So Bob makes a measurement again that gives random results. So here I have a probability 1/2 and 1/2. And same here. Okay. And so if I compute all of these 4 here, they are all the same. You see this is 1/2 times 1/2 times 1/2. So it's 1/8, 1/8, 1/8, 1/8. And now, so I have my two cases with an error that are here, and each one has probability 1/8. Okay, so what I conclude from this is that the quantum bit error rate in this case, it is equal to 25%. Okay, it's the sum of these two. All right, so you see that if Eve would make this attack, well, as our intuition suggested before, she will introduce errors, okay? And in fact, these errors, they are relatively likely. They are, 1/4 of the time. Now, the point is that Eve could, of course, decide in each round to do or not do this attack, right? Which would then reduce this error rate. Of course, if she will never do this attack, then there will be no errors, but then she learns nothing about the key. And so if she would do it with some probability, she would learn part of the key, but this part becomes, increasingly or decreasingly small, okay? So there is in fact a trade-off somewhere, and there is a sort of, one can, prove that there is a critical value of the Q bar, which is in fact 11%. Okay, and so below this critical value, so below the Q bar of 11%, Alice and Bob can provably establish a perfect private key. Okay, and in order to do that, they still need to do error correction plus privacy amplification, okay, that we will detail in a minute. So at this point, you might be a bit confused because we looked at some attack and we said here the error rate is 25%. And then I told you, in fact, the critical value for Alice and Bob to be able to establish secret key is 11%. So why is there such a big gap between the two? Well, of course, the reason is that here we considered one very specific type of attack. But of course, in general, in the protocol, Eve could perform whatever attack she wanted to here, right? She could use a quantum computer, for instance. She could do any operation that is allowed by quantum mechanics, in fact. And as you can guess, maybe this attack here, which is natural but also very simple in a sense, is not the best one. So there exists an attack which is much, much stronger and which would give full knowledge of the key to Eve if the Q-bar is about 11%. Okay, so we're not going to discuss this attack here because this is very complicated, but one can prove that this is the best attack. And so if you are below this critical value of the Q-bar, okay, then you can actually extract a perfect private key out of the, the sifted keys, okay? And again, so the idea is that this is, in the world of cryptography, this is really something completely new, because remember, in classical cryptography, there is a no-go theorem for establishing a private key between Alice and Bob that have never met, right? Now, in this BB84 protocol, we just detailed a specific protocol which allows Alice and Bob, even though they never met before, to actually distribute this private key. And Eve can really listen to the channel and, do whatever is allowed by quantum theory in order to try to extract information. And so that is a sort of type of security that is, it's not computational, right? This is a physical security. So if Eve was able to get the key for a Q-bar below 11%, Eve would somehow have to break the laws of quantum physics, okay? And of course, in quantum cryptography, this is an assumption that we make, that Eve is bound to the laws of quantum physics. But essentially, this is the only assumption we need to make on Eve, right? I mean, so coming back to a discussion before, of course, an additional assumption is that Eve cannot control the classical channel where A and B communicate, right? She can listen to that channel and copy all the information that is said there, but she cannot change what Alice is saying to Bob, okay? That is important. And of course, there is also an even more basic assumption in cryptography, but that is just for cryptography to make sense, is that Eve has no access to the labs of A and B, right? If Eve can just enter the lab of Bob, she can look at what is the key that he wrote down on his piece of paper, and then she knows everything. Okay, but that goes outside of the scenario of cryptography. All right, any questions so far? Okay. Okay, good. So then I continue. Yeah, I should, maybe one thing I could say is that, because now we derived, we announced, let's say, this critical value for the error rate. So you may wonder if this is anyhow relevant to practical implementation, because practical implementations have a sort of inherent error rate. Sorry if you hear noise. This are my daughters that woke up apparently, so I hope we can finish the lecture. Okay, let's see how it goes. So this 11%, this is something that allows you really to work in practice, right? So in a typical optical setup where you use photons and fibers, you can have error rates of about 5%, even on distances of about 100 kilometers. So that is, it makes it totally feasible in practice, and in fact, it is even accessible as a technology today. All right, so to finish, I will go now to, I will detail a bit error correction and privacy amplification so you get an idea how it works. So let's start with error correction. All right, so at this point, so now we did the basis reconciliation and we did the estimation of the error, right? So we know what is the error rate. And so now we have bit strings. So let me write them again, A and B. Okay, so these are the strings. So these are not the sifted keys, but it's after having subtracted the fraction I used to estimate the error. Okay, and so because there are some, because this error rate I estimated, I know what is the probability P. So this is the probability that AI is equal to BI. And I'm going to assume that this is larger than 1/2. Okay. So for every bit here in these sifted keys, I have this probability here that I call P for them to be equal. And this is larger than 1/2 because if it was smaller than 1/2, they would be more likely to be opposite. Okay. So it makes more sense that they are sort of, that they have a larger probability to be equal than being different. Okay, and if it was 1/2, it would be random. Okay, there would be no correlation between A and B. So this makes sense here. Okay, there is some correlations between my sifted keys. It's not perfect, but it's definitely not random strings. All right, so now we want to produce shorter keys with less errors. Okay, so goal, produce shorter keys, but with stronger correlations. Okay, so here is how the protocol goes. So this is our error correcting protocol. So Alice is going to calculate. So Alice computes a new variable that I call capital A that will be A1 plus A2. Okay, so here I just take the first 2 bits of these strings and I add them modulo 2. Okay, so this is addition mod 2. Okay, so Alice will compute this and announce. Okay, so she announces it to Bob, again on the authenticated channel. And so in the meantime, Bob does the same. So Bob, he computes B equal B1 plus B2 and announces. Or if you want, he doesn't need to announce, but he can check what is A, and then he will tell whether B is the same or not. Okay? So here is how it goes. So if capital A is equal to B, okay, then they keep, okay, and they find new bits. New bits, namely, let me call it A prime. A prime will be A1, and for B prime equal B1. Okay. Now, let me write it here. If A is different from B, they discard. Okay. Now, what is the point? So this is when it somehow when it doesn't work. Okay, so then they just discard and throw these bits away, and then they go to the next. Okay, so you see that this is a protocol that will indeed shorten the string, right? But now we said that, well, we announced that it will produce a shorter string, but with stronger correlations. So we could check, okay? So in particular, we have to compare the correlations of our new bits to the initial ones, okay? So we need to compute what is the probability for A prime to be equal to B prime, okay? And of course, that's the probability that A1 is equal to B1. However, yes, okay, so let's do that. So when is capital A equal to capital B? Okay, so of course capital A is equal to capital B when A1 is equal to B1 and A2 is equal to B2. Okay, in that case, in fact, A1 is equal to B1. Right. So that case has a probability P squared. Okay. Now, you see, there is another possibility that A1 is equal to B1. This is when A2 would be different from B2. But in that case, capital A will be different from capital B, and therefore I discard. So I don't need to consider that case. However, what I need to add here is a denominator, okay? Because A prime and B prime, they are not generated in every round. They are generated only if capital A is equal to capital B. So I have to renormalize by the probability. So this must be here the probability that capital A is equal to capital B. Okay, and this I can calculate. Well, I know that there is already a term P squared here, which is the case I described before, when A1 is equal to B1 and A2 is equal to B2. However, there is another possibility for these two to be equal. It is when A1 is different from B1 and A2 is different from B2. Okay, then because it's mod 2, capital A is still equal to capital B. And so that has probability 1 minus P squared. Okay, is the probability that the two of them are different. Okay, so it's 1 minus P squared. Okay, and now, well, you can immediately see with a little bit of algebra that this thing is always larger than P for P greater than 1/2. Okay. So I let you check this, but okay, it's immediate to see. And so the conclusion of this, is that we get more correlated keys. Okay. Now the point is they are more correlated, but they are not yet perfectly correlated. Okay, because this probability, although it is bigger than P, it may not be 1 yet. However, you see, I can bootstrap this protocol. I can make it several times. And at some point, the probability here will be as close to 1 as I wish. Okay. And, you know, if the probability that the two are equal is 1 minus 10 to the minus 26, then it's okay, right? They are perfectly equal. Okay, so that's the idea of error correction. Now, you see what is very important is that Eve, so here Alice and Bob have removed errors, but they did not leak any information to Eve, okay? Because capital A and capital B oops, sorry. So capital A and capital B were announced publicly, but A contains no information about A prime, okay, because of this relation here. Right, A2 is a random bit, and so therefore, if I know A, capital A, I know nothing about A prime unless I know A2 as well. Okay, so that is error correction. Any questions so far? Okay. Yes, okay, maybe in fact one can say we can in fact say exactly what is the reduction of the length of the key, right? Because we started from a key of length n, okay? First, we used 2 bits in every round, right? And so then we generated only a new bit in case capital A was equal to capital B. And that had probability p squared plus 1 minus p squared. Okay, so that is the, let me call this n prime. This is the length, so this is the length of the new key, okay, after error correction. So I reduce, but I get a key of much better quality. All right, so now we move to the last step, which is privacy amplification. And so as the name suggests, so the goal is to make sure Eve knows nothing about the final key, right? Because in error correction, right, so Alice and Bob improved their mutual knowledge or their mutual correlations in the key. But of course, if Eve knew already something about the initial keys, she can do all these steps also. I mean, she can follow this error correction and do it on her own version of the key. And so on that, on this key, she may still have some correlations with the key of Alice and Bob. Okay, she may still know something about it. So the last step of privacy amplification is to make sure that in the end, Eve really knows nothing, okay? So let's formalize that. We are going to say, so at this point meaning after error correction, Eve may still have knowledge on, let me just write A prime, okay, because now A prime and B prime are essentially the same. Okay, let's just say that they are the same. So here we are going to assume that after error correction, A prime is equal to B prime. Okay, so this knowledge of Eve, well, I can formalize it. I can say that the probability so E denotes the key of Eve, or her guess of the key, right? So the probability that E is equal to A prime, I denote this Q. This is larger than 1/2, okay? So if this would be 1/2, that would be great, right? It would mean that there is, the probability that E is equal to A prime, this is just random, right? This is just 1/2. Maybe I should put an index I here, because here I'm talking about every bit of the string. let me maybe do it like this. Okay, put indices A. So if for every bit of the string Eve has probability 1/2 to guess it, then we are good, right? Because the best Eve can do is just guess what the key is. And that is, of course, the thing we hope for, right? But at this moment, this is not the case, right? The probability that Eve knows the key is still larger than 1/2. So somehow, similarly to error correction, we will describe a protocol to define a new key from these A prime here. And on this new key, we will prove that Eve knows less, okay, than on A prime. That's the idea. Okay, so here is how we do it. We take, again, 2 successive bits. So Alice computes, let me call it, okay, so Alice computes as a new bit, let me call it A double prime. This is going to be A prime 1 plus A prime 2. Okay, so you see it's very similar to what I did before. I just call this A double prime now. Okay, and so contrary to before, this is the new key bit. Okay, and of course, because it's the new key bit, it will not be announced. So that's the difference with before, not announced. Okay, now in his lab, Bob does the same. So Bob computes B double prime, which is B1 prime plus B2 prime. Okay, and this also defines the new bit. All right. Now, because the strings A prime and B prime were already perfectly correlated, of course, we have that P of A double prime is equal, the probability that A double prime is equal to B double prime, this is 1. So for Alice and Bob, doing this doesn't decorrelate their keys, right? The new keys are also perfectly correlated. But, okay, if we look at Eve now, so what's the probability for Eve that E double prime would be equal to A double prime? Okay. Well, so you see, Eve has to calculate also the same thing as Alice and Bob. So she has to take her symbols EI here in order to estimate what is A1 prime and A2 prime, and then add them in order to get E double prime. Okay, this is what she does. Now, very similar to before, well, there are 2 cases in which E double prime is equal to A double prime. This is when E1 is equal to A1, so that has probability Q, and A2 is equal to E2, and that has also probability Q, so it's Q squared. And then there is another case in which Eve could guess correctly E prime. That would be, in fact, when she gets A1 prime and A2 prime wrong, both of them, right? So then I have a 1 minus Q squared. Okay, so that's the probability for Eve to know the new bit after privacy amplification, and you can readily check that this is strictly smaller than Q. Okay, so that is smaller than Q if Q is larger than 1/2. And in fact, you see, I guess this is in the tutorials this week, but this value here is strictly smaller than Q, And in fact, if you bootstrap this protocol, if you do it many times in a row, the final value here is going to converge to Q equal 1/2. Okay, so in the limit, Eve will know nothing about the key. So maybe let's write this. So in the limit, yeah, I don't know how to write this, but let's write Pn equal An. If you do this many rounds, this thing will tend to 1/2. Okay, and so this means that Eve knows nothing. Okay, I don't have the space to write about An, but clearly this is what I mean. Right? Okay, I hope it's readable. Yeah. And I hope it's understandable as well. I went relatively quickly through this, but these are just simple classical manipulations, but at least they give you the gist of the idea on how it works. Should also say that these are really the simplest protocols for error correction and privacy amplification. In particular, you see they are quite costly in terms of the factor of reduction of the key, right? Here we lose quite a lot, and in privacy amplification, well, no, in privacy amplification, well, we just lose a factor 2, okay? But it depends. If we have to do it many rounds, then we lose a factor, 1/2 to the n somehow, and so that is more severe. So in practice, there are better ways to do this, but the essence of the idea is just really the same. All right, so it's a good time to make a little break for questions. Is everything clear? Yes, okay. So at this point, okay, so in lecture 5, there is still a part on doing quantum cryptography based on entanglement. I guess because it's already 3:30, I can probably, there is no need for me to detail it here, but maybe I can just say a few words about it. So the point is that, as I mentioned at the beginning of the lecture, this protocol of BB84 went essentially unnoticed for almost 10 years until some physicist, Arthur Eckert, rediscovered somehow quantum cryptography in the early 90s. And in fact, he rediscovered quantum cryptography, but in a very different way. So of course, he was not aware of the work of Bennett and Brassard. And he had, in fact, a very different idea. Maybe I can just detail it here. So this is the idea of Arthur Eckert. So Eckert's idea. I think this is 1991. So Eckert's starting point was quantum entanglement and, in fact, non-locality. Okay, so you imagine that you make a setup here with an entangled, where you prepare an entangled state, and then you have Alice and Bob making measurements, and so we do like last time, we denote the choice of measurements X and Y, and the results A and B, and we saw that there, for some well-chosen entangled state and measurements here, we could get a joint probability distribution here that is non-local. Okay, so PABXY can be non-local. So the fact that it's non-local, this means that you know, the experiment cannot be described by a local, well, sometimes we say hidden variable model, right? So to be more concrete, it means that any model in which the information here, instead of being an entangled state, would be some classical piece of information shared to A and B. So no such model can explain what we see in our experiment, okay? And this non-locality can be detected, for instance, detected by Bell inequality violation. Okay, so now here is the idea of Eckert, which is quite a brilliant idea. So instead of thinking of, okay, what does it mean from a fundamental point of view, this effect of quantum non-locality, Eckert thought, what can I do with it? Okay, because it's there. So, you know, of course, it's interesting to think about the nature of this problem, but let's be more pragmatical. Let's think what we can do with it. And so then his idea was that the presence or the possibility to explain the data with some local or classical variable means that there could be, in principle, an eavesdropper here that, you know, produces the information sent to these labs. Okay, because if the eavesdropper can intercept the classical information, he can make copies of it, and therefore, if this information is meant to, you know, establish a key, then Eve could know the key. All right, but now the converse is interesting, right? Because if the statistics that Alice and Bob see is non-local, well, then they know that it is impossible that these correlations were mediated by a classical common cause, right? So there can be no local hidden variables here that explains this behavior. And so because that is the case, Eckert argued that this must mean that the statistics or the results of Alice and Bob here, they are sort of private in a sense, right? So it would be impossible for an eavesdropper to guess what results they are actually going to get. Okay, so here is maybe let me just write this. So the idea of Eckert, so the idea is that the absence, or if you want, no, it's not the absence, but the impossibility of describing or having local variables means that there was no eavesdropper. Okay, or maybe said in more clear terms, it means that a potential eavesdropper could not know what the results of these measurements are. Okay, and now that doesn't yet tell me that the measurement results are correlated, which I would need, right, to establish a key. I would need that A is equal to B somehow. But, you know, if you consider again this entangled state here, and you just imagine that you do measurements in the same basis here and there, then you easily see that you get correlated results. So if you would combine this with a Bell test, okay, which would ensure the absence of local variables in your experiment, well, then you can sort of argue that the output strings you get can be used for to build a private key. Okay, so that was the intuition of Eckert. It was not proven formally in his paper, but this turns out to be true. Okay, so later on this was proven. And in fact, it's interesting because you see at this level, it seems like this protocol of Eckert here is very different from BB84, okay, because it's based on entanglement and non-locality. But in fact, at the end of the day, it's essentially the same, okay? So in that sense, you know, Eckert really rediscovered quantum cryptography, but in a slightly different way that is also very insightful. And so if you look in the lecture notes, this is discussed in a little bit more details. And it also gives you somehow the idea on how you really prove mathematically the full security of quantum key distribution. This is in general something quite complicated, so we didn't do it here, but instead we got the intuition as to how it must be secure. All right, so let's end here. Are there some questions? Don't be shy.
Do I have a question?
Ah, good, yes.
So without the error correction and the privacy amplification,
Mm-hmm.
it seems that Eve could have like 20 or 24% of the message if she uses this technique and say, Alice and Bob decide to, you know, if they have less than 25% agreement on their key, then they say, oh, we're safe. And then Eve has 25% of the key. It seems to me that without error correction, she can reconstruct 25% of any message. Is this correct?
Yeah, so let me come back to this. This is the slide where corresponding to your question.
Yeah.
Yes, so indeed, in this intercept resend attack, the error rate was 25%.
Yeah.
So, you know, if Alice and Bob see a 25% error rate, what can they conclude? Well, they can conclude that it may have been the case that there was an eavesdropper and that Eve implemented this particular attack here.
Right.
Okay. And so in that case, you see that, of course, after basis reconciliation, right? So Eve would indeed know something about the key, okay? And then you can actually prove that there would be no way for Alice and Bob to extract a private key out of this data, okay? So as soon as the error rate is compatible with an attack like this, right, where Eve gets a significant amount of information, then you have to abort, okay?
Right.
But that is not a problem to abort, right? Because all you do here is to try to distribute the key. So if Eve knows the key, well, okay, she knows a bit of the key, but you know that this key is compromised, so you will not use it in the end.
So the only case where you would continue is if the quantum error is lower than 11%.
Yes, so you will only continue if the Q bar is low enough. Okay, and here I just gave you the result essentially, because this 25%, it was derived for this attack here. But this attack is the most natural you may try to use, but it's not the best. There is something much better that gets to 11%. Okay, but you can prove mathematically that below 11%, there is a way for Alice and Bob to establish a perfect private key. Okay, So that means that no matter what Eve does, okay, limited by quantum mechanics, of course, she can still not get the key in the end, right? So the best thing she can say about the key in the end is to try to guess it.
I see. But also this this 11% that you give here, doesn't it depend on the number n that you start with? Because if you have not enough bits from the start, you cannot do the error correction so much.
Sure, yes. No, so if you, but that would be that you do the protocol badly, no, somehow. If you just send 3 qubits, of course, it's not going to work. So typically you go backwards, right? You say, okay, in the end, I would like to have a key that is the same length of my message, so maybe 10 million bits, okay? And so once you know that, and you know, via some of the estimates we made, you know what is going to be the shrinking factor, right, between the initial key and the final one. So therefore, you know how many rounds of qubits you have to distribute to start with.
Okay.
You see what I mean? But you're right, this is, I mean, you see, in practical schemes, the speed or the rate of these devices is typically megahertz. Okay, so per second you send millions of qubits, and probably in the end you extract a key that is typically kilohertz, or maybe tens of kilohertz.
I see.
But of course, how much you have to shorten the string will crucially depend on the qubit, right? If you have 1% error, of course, you need to perform much less error correction than if you had 10% errors.
Right.
Okay.
Thank you.
Yeah, you're welcome. I see another question. If I can scan and upload the notes. Yes, I can do it. Okay, I'll do it. You can also, so I will also put the video again on YouTube as last week. But if you find it helpful, I can also scan the notes. Well, I should also say that in the lecture notes, right, in these ones here, okay, you find more or less the same material as what I discussed, okay? But sure, I will do that. Any other question? All right, so if not, I stop this and I cut the recording.